Hello, everybody. This is the problem solving session. It's a tutorial section for the Maths2501 linear algebra or Math2099 linear algebra at the University of New South Wales. That's the week 4 work that we do in our class. This is just a recording for that tutorial week 4 work for my students who missed or would like to have some videos that they can watch later on to learn more. That's the purpose of this video. So let's start. So basically what we've done in week 4, the topics to cover is Gram-Schmidt process, QR-factorization, orthogonal complement of a vector space, and the projections of a subspace W on W complement, and the least square approximation. In this video, I will focus on first two sections, and then the next video will be about other points here. This section here is about to reminding ourselves this is a general knowledge and everybody needs to know this by now, but just remind ourselves what we need to know, what should have need to know. So a unit vector, you can always obtain a unit vector in the direction of u. So you have a vector in a direction, but it is long or short than the unit. It is not the one measure. If you want to make it a one measure, then you need to divide that vector to its length. If you take the length function of this, you will always have 1 because the length function of this and the length function of this will be the length function of it. So if you take the 12 length function, it will not differences. The length of this vector will always be 1 for every vector. So you can always find a unit vector in the direction of any vector by dividing its length. So this is what it says. If you want two vectors are perpendicular together, if and only if their dot product is equal to 0. You can express the dot product as a matrix multiplication. This is for the real vector spaces. So here we have the transpose. If you have U as a column vector, that's how we think about our vectors in the real vector spaces. In Rn, in Euclidean vector spaces, what I mean by that. And then if you take the transpose, then you have a row vector. If you have the row vector and a dot product with the column vector, it's a matrix multiplication. So this means the dot product with that's basically the definition of a matrix multiplication. So the dot product here can be written as a matrix multiplication. Be careful with your notation because if you put the dot here, it represents dot product. But we have nothing here. If you put dot here, it is an illogical step to do it because it is not a dot product. If you're making a row column, row vector, multiply with the column as a dot product does not make sense because dot product is not defined in net space. Dot product is defined with row or column vectors. You need to choose from the beginning of your calculation which type of vectors do you do. So we usually work with the column vectors. So the column vectors to the column vectors dot product here has a meaning, but if you put the dot here, you destroy the meaning of the matrix multiplication. And it will not make sense because you have a transpose here. So be careful with your notation. This is why I'm expressing here. Okay, so if you have a dot product, express it with dot. If you don't have a dot product, don't use anything for multiplication. The angle between two vectors, U and W, can be computed by this equation. A vector perpendicular to both vectors, V and W, is defined as a cross product. This is just a reminder, you know what a cross product means. And we remind ourselves is that the projection of V onto a vector W, which we denote this projection of the vector V on the vector W. So this will be a real multiple of the vector W. So V here dot product W and divided by W dot product W, or you can think of that as a square of the length function, length of the vector W. So this is a vector notation here, needs to be put. Okay, then so this is a real number, so it's a multiple of W's. Always that's what we found, because when you have a vector, you think about a plane, and you have a vector there, you're putting your vector projecting onto that vector, it will be either shorter or longer in the direction of that vector. Okay, so now this is just an introduction, just as reminding ourselves what we all need to know about it before we do the work today. Okay, this is a general knowledge, general process of the Gram-Schmidt process. I'm going to remind you what it is about and how to do it. And then we will have an example on how to do it. So Gram-Schmidt process, if you have any basis of the vector space, that's the process that will help you to find out an orthonormal basis, right? An orthonormal basis from any given basis. So we have a given basis here. Then if orthonormal basis means that it is orthogonal, means that all of the vectors are orthogonal each other, they're perpendicular each other in the basis. And also their length is 1. This is orthonormal basis. Orthogonal basis means that the bases with every vector is perpendicular together, each other, but the length does not mean that it will be 1, right? That's what it means. That's the differences between orthogonal and orthonormal. So first thing what we do, we find orthogonal bases from any given basis. So this is the first part of this process, is about to obtaining an orthogonal basis. First vector, assume the first vector, say V1. Now the second vector we calculate as x2, second vector here, minus projection of the first vector on the first vector of x2, which is the second vector here. With this definition, when we calculate this vector, the vector that we found will be perpendicular to the vector v1. And v3 will be the x3 minus the projection of this projection of x3 on v1 minus the projection of x3 on v2. When you calculate this vector, you will find the vector which is perpendicular to v2 and v1. So with this kind of processing, we eventually, whatever the dimension is, how many elements you have in your basis element, you will find an orthogonal basis, which means that all of those vectors are perpendicular together, but the length of the vectors may not be 1. Now, next step is very important. We normalize it, which means that every vector here you're taking, you're dividing by its length. Now, UIs will be the orthonormal, will give you orthonormal bases. And that is the Gram-Schmidt process. Gram-Schmidt process is related with the QR factorization. Let me talk about the QR factorization. In this case, assume that you have a matrix, A matrix with the P rows and Q columns, and the row columns of this matrix has linearly independent columns. Then there exists a Q matrix, which consists of the orthogonal columns, and R matrix, which are invertible upper triangular matrix. So basically, such that A can be written as a matrix multiplication of QR. And the Q, now we want Q to be an orthogonal matrix. If you want an orthogonal matrix, you must have orthonormal bases on the columns, right? So I should have said here orthogonal matrix or Q, but also I keep this note in general form, but when we are doing it, we would like to have orthonormal bases in Q, and R will be the upper triangular matrix. Okay, and this orthonormal basis we will obtain by using the Gram-Schmidt. Now let's do all of this together, which means that we would like to find out the QR factorization of this matrix by using the Gram-Schmidt method. Right. Okay, the column, I just named the columns. Column 1 is x1, column 2 is x2, column 3 is x3. So first thing to do is to find out the orthonormal bases, and then we will find the matrix Q by just putting those orthonormal basis vectors as a column, and then we will figure out the upper triangular matrix that will give us the QR factorization of this matrix. That's the aim of the game. And this will be the structure. So I said it before, but this is what we are going to do. It will be much more clear in the end of the exercise. So, x1, x2, x3 are linearly independent. It is because none of them, if you look at, for example, the first row, if you have lambda 1, lambda 2, lambda 3, this is equal to 0, and this has to be equal to 0. It is impossible, right? You cannot obtain, right? For example, if you say lambda times x1 plus mu times x2 is equal to x3, then you have one equation with this minus lambda plus 7 mu is equal to 11. And then on the other hand, you have 8 lambda plus a 7 mu is equal to 11. So it's a contradiction. It is impossible, which means that none of these vectors can be written as a linear combination of other. So it is immediately you can, by just looking at those vectors, it is not, may not be obvious in general, but it is in this situation, they are linearly independent. So we have x1, x2, x3 are linearly independent vectors. So that is a basis for the column space. So, okay. Then once we know that they are linearly independent, then we can start doing the work, applying the Gram-Schmidt process so that we can find the QR factorization. Gram-Schmidt method says that the first vector x1 is equal to v1. Second one, we need to calculate the x2 minus the projection of v1 x2. So the projection of x2 on the vector v1 will be the coefficient of the vector v1. These are the dot products. And we calculate the dot products. This number will be 81 and this number will be 81. And then we have really v1 here. So v2 is this vector when we calculate as a number. And v2 is, in fact, is x2 minus v1. We can also write x2. This will be helpful in the end because our aim is to find out the QR factorization. So then if you think about what is x2 in terms of v1, v2, that will be x2 is equal to v1 plus v2. v3, by the Gram-Schmidt method that we've just talked, x3 minus the projection of the vector x3 on v1 minus the projection of the vector x3 on v2. Now calculate these projection vectors. So that is the It will be a multiple of V1 because this is a projection on V1. And the multiple can be found with this dot products, x3 dot product v1, v1 dot product v1. We calculate this one above. That's 81, x3 dot product v1. This is x3 dot product x1. If you calculate it, you will see that's numeric v1, 81. So this is just really v1. And if you calculate projection of v2 on projection of x3 on v2, then that will be a multiple of the vector v2. And the multiple here will be obtained by the dot product x3 dot product with the v3 divided by v2 v2. And if we calculate it, it's all turned out to be 81, which is just happens with this example. It is not usually the case. It will be different in many different things, but it makes our life is very easy for this particular example. And then V3 will be this particular vector because this is x3 minus V1 minus V2 will give us this. In terms of x3 in terms of the V1, V2, V3 will be x3 is equal to V1 plus V2 plus V3 because I'm taking those ones onto the other side. So we found V1, V2, V3. If you check, it is always a good idea to check in this example because usually these examples are really the long examples. And if you make a mistake on the way, it will cause a lot of problem in the end, of course. So it is, as a good mathematical practice is also check your calculations as much as you can. So if you come to the stage, what theory tells us that these vectors are orthogonal bases. Orthogonal means any two of them, when we make the dot product, it has to be 0. So this times this is really 0. This dot product with this is 0. This dot product with this is really 0. We know that the lengths are not 1 because it's orthogonal. We need to check that now. Now we need to find out orthonormal. This process is called normalize it. Don't forget to normalize it. It is very common error not to normalize. You come to here and then you put those ones into the queue. It is not correct. Okay, please, please normalize. Don't forget to normalize it. So if you calculate the length of V1, that is 1 square, 8 square, 4 square, and the square root of all of those. So that's the length of V1. That is 9, and V2 is the same, 9. And V3, if you calculate, you will find 9. And it means each of U1, U2, U3 will give you orthonormal basis, where UIs will be 1 over 9 VI, for I is equal to 1, 2, 3. Now we are going backwards. We found everything that we need to find out is about the orthonormal basis. So that is the Gram-Schmidt. Gram-Schmidt ends in this row. Okay, this row, end of the Gram-Schmidt. Now we are focusing on more to find out QR factorization. Now we found here, I am taking these equations down. So x is 1, the red squared ones. x1 is equal to v1, x2 is equal to v1 plus v2, and x3 is equal to v1, v2, v3. I'm getting that, collecting those equations. And I know that each of the UIs is 1 over 9 VI. So the VIs is 9 UI. So this is what I am doing here. V1 is 9 U1. And V1 is 9U1, V2 is 9U2. It's coming from here. It's like a backwards. V1 will be 9U1, V2 is 9U3. As you see, so this is, we can write these ones in as matrix multiplication. Right? This is all I am doing to find out the QR factorization. I'm writing down these equations as matrix multiplication. I have equation x1 is equal to 9u1, x2 is equal to 9u1 plus 9u2, x3 is equal to 9u1, 9u2, 9u3. Okay, so this is x1, x2, x3 is equal to. This row with this column as matrix multiplication gives me 9u1, which is the first equation. Now this row with this column gives me 9u1 plus 9u2, which is the second equation. The last equation is this row with this column, 9u1 plus 9u2 plus 9u3, which is this equation. As you see, this is the consist of the orthonormal, the columns consist of the orthonormal basis, and this is an orthogonal matrix, and this is upper triangular matrix, not uni, upper triangular matrix. So we found this is Q and this is R, and these are the factorization of the matrix C that we started with. And here we have the U1, U2, U3 is given by. In general, of course, you don't have to, these numbers are exactly the same. So you will have something, 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 something here. Upper triangular means is, something, 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 something here. And the zero is below the diagonal. Diagonal and above the diagonal is some numbers, and below the diagonal is zero. This is called upper triangular matrices, and the R matrix could be any upper triangular matrix in general form. We don't have to get these ones. Just these numbers turn out to be in that way. I think that is clear for everyone. Yeah, I think that's all I want to do. I don't want to mention anything else. Yeah, okay. That's for this video. Thank you very much for listening, and hopefully it is helpful for everyone. Thank you.